Hello. I would like to begin by thanking the organizers for giving me the opportunity to speak in this format. This talk is about Bornological Dcap modules on rigid analytic spaces. There has already previously been a definition of coadmissible Dcap modules by Konstantin Ardakov and Simon Watsley. And the aim of this talk is to extend their framework to a much larger category, which allows for a derived formalism where we can then talk about derived functors and D-module theoretic operations. And towards the end, we're also going to see a derived analog of the notion of coadmissibility and prove some stability properties of this subcategory under the operations introduced so far. Let me begin by give you a couple of key points that are important for D-module theory, no matter in which geometric context. Now you can talk about D-modules really on any kind of geometric space you like. You can do this on varieties, on schemes. You can do this with complex manifolds. You can talk about arithmetic D-modules or D-dagger modules in a characteristic P setting or on formal schemes. It's mainly due to Berthelot. And as I already said, there's also the theory of Dcap modules by Ardakov and Watsley to talk about D-module theory in a rigid analytic context. In all of these geometric setups, a D-module is basically an O-module with a compatible action of the tangent sheaf, which then generates an action by arbitrary differential operators on your space. I'm going to make this much more precise later on, but now I really just want to highlight some characteristics that all these different theories either share or are at least aiming to encapsulate as well. So let me point out three important aspects that work when we're working with D-modules on smooth complex algebraic varieties, which is not surprisingly the geometric setup in which the theory works best. So the first point is that we can use D-modules to study algebraic representations or representations of algebraic groups of their Lie algebras in a geometric way. To be precise, there's a theorem due to Beilinson-Bernstein, also Brulinsky-Kashiwara, called Beilinson-Bernstein localization. If you take a semi-simple algebraic group over C or over some other algebraically closed field of characteristic 0, you can associate to it a variety, the so-called flag variety, by picking a Borel subgroup B inside G and considering the quotient G mod B. So if G is SL2, for example, and you can take as Borel subgroup the upper triangular matrices, and this coset space G mod B becomes isomorphic to P1. And the Beilinson-Bernstein localization states that there is always an equivalence of categories between the category of coherent D-modules on the flag variety on the one side, and on the other side, Lie algebra representations for the Lie algebra associated to G, which are finitely generated as a module over the universal enveloping algebra. And this extra 0 that is there is indicating that these modules need to have trivial central character. The functor between these is just take global sections. So this is actually looking quite similarly to the relation between quasi-coherent O-modules or coherent O-modules on some affine scheme and the corresponding categories of modules over the global sections. This theorem can be viewed in some sense as one of the foundations of a whole area of research now called geometric representation theory, because it allows us to interpret a representation geometrically as a D-module on a flag variety, which then opens up representation theory to many geometric tools. What are these tools? That's kind of the second bullet point of key aspects of the D-module theory. If I pass to the bounded derived category of D-modules, I can make sense of 6 functors that I am not going to formally define in detail. Let me just say there is a direct image functor, there's an inverse image functor, there are their Schrieg versions, so extraordinary, direct, and inverse image. There's a tensor product over O that still carries a D-module structure via a Leibniz rule, and there's a duality operator. Again, I'm not going to say what these operators do, but let me point out that, for example, if my morphism F is an open embedding, for example, then direct image and inverse image are really just restriction and push forward. In general, if my morphism F is something more complicated, then these functors get actually significantly more complicated in the sense that they are really only living in the derived world. It's not even that they are the derived functors of some functors working between the abelian categories. They are compositions of such functors. For example, note that if I have my morphism F, if I go along it, it's not just the structure sheaf that changes. If I go from X to Y, it's also the tangent sheaf that changes. So in order to have a D-module direct image operation, there's kind of a 2-step process needed. You first tensor with what is called a transfer bimodule, and then you take the push forward. So this is honestly a composition of various derived functors. Turns out these 6 functors are not preserving the condition of being coherent as a D-module, but thankfully there are other notions of finiteness that we can play with here. As I said earlier, any D-module is an O-module with some extra structure. So in particular, I could be very strict and require things to be coherent over O. In that case, you just get vector bundles with integrable connections. And sitting between coherence over O and coherence over D, there is a third finiteness notion called holonomicity. And it turns out that this class of holonomic D-modules, this is actually preserved under the 6 functors I described above, in the sense that the subcategories consisting of bounded complexes with holonomic cohomology are preserved by these 6 functors. So putting these 3 aspects of D-module theory together as a Beilenson-Bernstein localization theorem, we have 6 functors on the derived categories of D-modules, and these preserve the notion of holonomicity. These 3 things together really allow us to view D-modules as a very effective tool for studying representations. Right? I can not only interpret representations geometrically through the Beilenson-Bernstein localization, I can also manipulate them geometrically using these functors. And using stability of holonomicity, I can manipulate them, I can construct them without leaving the realm of finitely generated or coherent objects. As long as I stay holonomic, whatever I do to it, it always will remain holonomic, and in particular, therefore, coherent. So these 3 points work for smooth complex algebraic varieties, and the aim is essentially to also have things like this in the other setups. So let me briefly tell you what my geometric setup is going to be. I'm going to consider K as my base field, a finite extension of QP. I take R to be the valuation ring of K, and I'm going to pick a uniformizer pi inside R. As I mentioned earlier, Konstantin Ardakov and Simon Watsley have already defined coadmissible Dcap modules on a smooth, rigid analytic K variety. The coadmissible here I'm going to explain in a minute, but it's really, you should think of it as the analog of what coherent D-modules were earlier in the other setting. They also showed for coadmissible Dcap modules an analog of Beilinson-Bernstein localization. So there is a p-adic analytic version of the first bullet point. And this talk is essentially going to be about the second bullet point. So I'm going to give you a derived category of Dcap modules in which we can define these 6 functors. I'm not going to say anything in this talk about the third bullet point, about holonomicity and stability under the operations, because that's still work in progress. So let me first tell you how these coadmissible Dcap modules work by first of all reminding you of what differential operators look like classically. So just on the complex plane, algebraic variety A1, you know what differential operators are. They are finite sums, polynomial expressions in 2 variables, my polynomial variable x, and a second polynomial variable differentiation, d by dx, which I usually just write as partial. These finite sums live inside the endomorphism ring of my polynomial algebra C of x. In particular, this is not a commutative ring under composition. These 2 polynomial generators, x and partial, do not commute. Their commutation relation is dictated by the product rule. Viewing all these elements in the endomorphism ring means that the element little x, for example, just means multiply a function by x. So in particular, the expression partial times x means first multiply by x and then differentiate. So the product rule tells me that this is the same as the operator x times partial plus 1. In particular, this now links up nicely with what I said earlier, rather vaguely, about D-modules being O-modules with an action by the tangent sheaf. A module over this ring, of course, is just going to be a module over the polynomial algebra Cx, and then I need you to know additionally how partial acts. So it's an O module together with the information of an action by partial, which is satisfying a compatibility in the sense that it's satisfying this relation dictated by the product rule, that all the commutation relations are fine. If I have some open subset of my complex plane, I can, of course, make sense of differential operators on that open subset by just allowing more functions to appear. Right? I could have poles outside of my open subset, and this gives me then the sheaf of differential operators. And then, of course, I'm really talking about sheaves of D-modules, which are just quasi-coherent O modules with the additional partial action. If you look at this just in terms of what the elements look like for this ring, C, X, semicolon, partial, as I said, this is non-commutative, but leaving the non-commutativity aside, this looks a lot like polynomials into variables, which are precisely the functions on the cotangent space of A1. The cotangent bundle is trivial, trivial of rank 1. So we get that the cotangent space is just A2 or X times A1. So leaving aside the non-commutativity, this ring looks very much like the functions on the cotangent space of X. And it's this idea that we're going to carry forward when we are discussing differential operators in a p-adic analytic setting. What should differential operators be if I work on a rigid analytic space? Well, again, I'm just going to tell you for the easiest possible space. So let's consider the closed unit disk, the corresponding ring of analytic functions are then power series in one variable which converge. So the coefficients tend to 0. As we are in a non-Archimedean setting, convergence is assured by just letting the coefficients tend to 0. This is a Tate algebra in one variable. What should be the ring of differential operators on this closed disk? They should be power series in two variables, X and partial, again with the same non-commutativity relation that we had earlier. And the convergence condition on this power series ring should be the same convergence condition that I can find on the cotangent space. Cotangent space is again X times A1. So I already know what the convergence condition on X is. It's the same as in the Tate algebra. The convergence condition in the cotangent direction, so the convergence condition for partial, is going to be the one it converges on the whole of A1, i.e. it converges on closed disks of arbitrarily large radius. So my ring of differential operators that I write as Dcap of X, this is going to be an inverse limit over various non-commutative Tate algebras into variables where the second variable, partial, gets repeatedly rescaled to get functions converging on disks of radius norm pi to the minus n as n tends to infinity. This is the ring of differential operators that we are considering here. So just from the setup, this looks very much like the space of analytic functions on a Stein space on X times A1. So we should exploit kind of an algebraic framework describing algebras that look like functions on Stein spaces. This definition is due to Schneider and Teitelbaum. If I have a K algebra A, I call it a Schrdingerstein algebra. It's the inverse limit of Noetherian Banach algebras, such that the transition maps are all flat. So AN is a flat AN plus 1 module via this morphism, and all the transition morphisms have dense image. So, for example, just going back to the case of the analytification of A1, this is the functions on there are the inverse limits of the corresponding functions on disks of larger and larger radii. So there's an inverse limit of Tate algebras, Noetherian Banach with flat transition maps with dense image. the corresponding notion of kind of a coherent module is the notion of coadmissibility. For a Schrdingerstein algebra A, an A module M is called coadmissible if it's the inverse limit over finitely generated modules over these Noetherian Banach algebras AN, such that they are compatible in the sense that going from Mn plus 1 to Mn induces an isomorphism. Mn is just given as the localization. It's An tensor Mn plus 1. So again, if these were literally functions on some Stein space, then this would correspond to the notion of a coherent O module on that Stein space. Even in the non-commutative case, this category of coadmissible A modules is always an abelian category with many nice properties. Essentially, it's an analog to how finitely generated modules work over Noetherian Banach algebras. So the theorem that gets the Dcap module theory off the ground is the following. If I have any smooth affinoid, then the corresponding ring of differential operators Dcap of X is indeed a Schrdingerstein algebra. And if I pass to some affinoid subdomain, then I can do this via some exact localization functor that is given in terms of a suitably completed tensor product. This tensor product you can write down purely algebraically because it's just you take the tensor product on the Noetherian level and then take the inverse limit over these guys. So this gives a functor from coadmissible Dcap of X modules to coadmissible Dcap of U modules. And as I said, this localization is exact. So in particular, you have everything in place to set up a theory of coadmissible sheaves of Dcap modules exactly in the same way as coherent O modules work. Okay, you are considering sheaves of Dcap modules which are locally given as localizations of coadmissible modules on affinoids. So this theorem was proved by Arakov-Wotsley with some additional conditions on the affinoid. It works, for example, if the affinoid has a free tangent sheaf. So in particular, it always works locally. But that this really is true on every affinoid. I generalized this a bit. Okay, so this is the kind of the basic category that you can play with strictly analogously to the category of coherent D-modules in the complex algebraic setting. As I said earlier, it is also for this category that we have a Beilenson-Bernstein localization result. So coadmissible Dcap modules on an analytified flag variety will correspond to a certain class of coadmissible Lie algebra representations with trivial central character. There's also an equivariant version of this to actually get the semi-simple group into the picture. And this kind of explains the terminology. So these coadmissible objects will dually correspond to admissible locally analytic representations. The problem or kind of the limitations of this theory are, of course, that if I just have coadmissible Dcap modules, it's very, very hard to do anything on the derived level. Okay, it's not quite clear how you get suitable resolutions to actually introduce derived functors. I guess a priori you could try and work just with kind of algebraic objects, so literally just abstract Dcap modules. But just looking at this theorem, you already see that at some point you probably want to have something like derived completed tensor products. So we need some analytic or topological category of Dcap modules that still allows for a good derived formalism. That's the aim. We want to have a derived category of Dcap modules where we can do things like a derived completed tensor product, and then we hope to actually introduce all the derived functors for this derived category so that we get 6 operations. So let me introduce the corresponding categories I propose. The first thing to learn is what's called a Bornology or a Bornological vector space. This is just the formal definition. The idea is that a Bornology axiomatizes the notion of a bounded set in the same way how topologies axiomatize the notion of an open set. So a convex Bornology on a vector space is a collection of bounded subsets such that a singleton element is always bounded. A finite union of bounded sets is still bounded. The R span of some bounded set is bounded. This is what the convexity refers to in the definition, but for me, everything will be convex. A rescaled version of a bounded set is still bounded. So for any scalar lambda in K, lambda times a bounded set is still bounded. And if I have a subset of a bounded set, then that's also bounded. I can turn this then into a category by considering as morphisms those K-linear maps that send bounded sets to bounded sets. I guess at this point I should say that in some sense you have seen several examples of such Bornological spaces already, because if I give you, say, a normed space, a Banach space, or even a semi-normed space, you already know what I mean by a bounded subset. It's something that is bounded with respect to the norm. And then, of course, the condition of the linear map being bounded corresponds to the condition of being continuous. So you can actually extend this example quite a bit. If I take any locally convex topological vector space, so this is a topological vector space that is given by a family of seminorms rather than just a single seminorm, then I can put a Bornology on this by just considering those subsets that are bounded with respect to each of the individual seminorms on this vector space. So this gives me actually a functor from locally convex topological vector spaces to Bornological vector spaces. There's also a functor going the other way, by the way, from Bornological to topological. These two are not an equivalence, but they are an adjoint pair of functors. So this notion of Bornology is very, very close to the maybe more classical notion of locally convex topological vector spaces. The advantage that we have is that this Bornological category has a tensor product which is much better behaved. We're going to see this in a second. So I'm actually not going to take Bornological spaces. I'm going to restrict down to complete Bornological vector spaces. So this will, this notion of completeness essentially corresponds to what you understand to be completeness in topological vector spaces. So the images of Banach spaces and Frechet spaces under this Bornologify functor will naturally be complete Bornological vector spaces. Okay. So the following proposition, this is due to Schneiders and Grossman-Schneiders, is kind of summarizing what the essential categorical properties of this category of complete Bornological vector spaces are, it has all limits, it has all co-limits. The crucial thing is actually quasi-abelian, which means it's close enough to being abelian that you can form a derived category which is well behaved. All of these kind of topological categories, you have no hope of ever getting something that is an abelian category, so this is the best we can hope for. It's a quasi-abelian category in the sense of Schneider's. It has enough projectives. To get enough injectives, you need to pass to what is called its left heart, or its abelian envelope. For any quasi-abelian category, there is an abelian category to go along with it that actually has the same derived category. And so in this case, it turns out that this abelian envelope, this left heart, has enough projectives, and it's a Grothendieck abelian category, so in particular it also has enough injectives. And as I said earlier, an additional advantage of this category is that the tensor product is well behaved. So you can extend the completed tensor product on Banach spaces to give rise to a completed tensor product on complete Bornological vector spaces. And this actually gives the category the structure of a closed symmetric monoidal category. So the tensor product behaves as it should, and there's an internal Hom functor as its right adjoint. So having these categorical properties in place, that is essentially what gets the theory off the ground, that we can talk reasonably well about sheaves valued in this category, then about a sheaf of rings with values in this category and the corresponding module categories. So we already saw that over an arbitrary smooth affinoid, the sections Dcap of X were Frechet algebras. So in particular, I can view them as complete Bornological algebras, and then it's not hard to show that this actually defines a sheaf of complete Bornological K algebras on any smooth rigid analytic K variety. So once I have this, I can actually form the corresponding module category. So this is literally the category of complete Bornological Dcap modules with a bounded action. And just building on the previous proposition, it's straightforward to show that this is again a quasi-abelian category. It's complete and co-complete. Because this is a category of sheaves, we will not find necessarily enough projectives, but we find enough flat objects with respect to completed tensor product over Dcap. And as before, we have enough injectives once we allow ourselves to pass to the left heart, to pass to the abelian envelope of this category. Okay, so the upshot of this is that we can form the derived category of this, because this is a quasi-abelian category. So this has an actual derived category. This admits flat resolutions. It admits injectives resolutions if I view it as the derived category of the left heart. So I can always derive my tensor products, and I can right derive my left exact functors whenever these left exact functors actually extend to left exact functors between the corresponding left hearts, that we can often do with help of the adjoint functor theorem. So having this theorem in place just allows us to formally form the derived category and derive functors, all the standard functors that we might have, a push forward, a pull back, a completed tensor product, an inner Hom. And so just putting these together in the same way as they work for complex algebraic varieties, we can then define analogs of the 6 operations we had earlier. Okay, we can define a direct image, we can define an inverse image, We can define a left-derived completed tensor product over O. The duality is given as an R hom into Dcap itself and then suitably side changed. So all of these things now make sense as derived functors on the derived category of complete Bornological Dcap modules. So up to here, this is just purely formal category theory to make sure that this derived category is kind of behaving in a natural way. Of course, I can't make any claims about how well behaved these 6 functors are on this level, because this category is incredibly large. It's not just that I'm considering everything that is complete Bornological. There is no quasi-coherence condition whatsoever. These are all possible sheaves of modules. It's very difficult to make any good statements about how these functors behave on this very large category, apart from some more obvious results about, for example, composition for direct images or composition of inverse images. But in general, as I said, this category is too large. We want to restrict further down to something that essentially works like, well, the category of complexes with coadmissible cohomology, right? Something that plays the role of what would be bounded complexes of D-modules with coherent cohomology in the complex algebraic setting. Before we do this, I should briefly say that this notion of complete Bornological Dcap modules is really compatible with the theory as we had it so far, in the sense that just as I could view Dcap as a complete Bornological sheaf, obviously looking at the corresponding Frechet structures for coadmissible modules as a Bornological structure, I can write down a functor from coadmissible Dcap modules to complete Bornological Dcap modules. And this functor is always going to be exact, fully faithful. And it turns even out that the completed tensor product that we saw in the previous section when we talked about localization for these modules, this is literally the corresponding completed tensor product in the complete Bornological world. So everything is compatible and everything makes sense. Okay, so now that we have this, coadmissible modules live naturally inside complete Bornological Dcap modules. Now we can try and kind of get the same thing on the derived level. I want to have a derived category that plays the same role, or sorry, a triangulated subcategory of the derived category that plays the role of the coadmissible guys here. So let me do this by basically just copying down the definition of coadmissibility and writing everything in a derived way. So if I have an affinoid X, I'm going to call a complex a C complex if all its base changes to these Noetherian Banach levels D sub n are actually bounded complexes with coherent cohomology, and these coherent guys match up in the correct way, in the sense that the cohomology of M is given as the inverse limit of the cohomologies of the Mn of these coherent guys. You might wonder why I don't write this second condition really in the derived sense. So why I not write that the natural morphism makes M a homotopy limit of these localizations. The reason for this is a bit subtle and has to do with the fact that these Noetherian Banach guys Dn actually only define sheaves of rings on suitable subsites of my Grothendieck topology. The site changes as I go from one level to the next. So really, to make sense of this on a Dcap level, I can formally define this inverse limit of individual sheaves, but I can't do this on the level of complexes. Alternatively, I guess one could form the equivalent condition that M is the homotopy limit of these MNs via the natural morphism in the derived category of complete Bornological K-vector space sheaves, so without any module structure. Anyway, so we're really just writing down kind of derived analogs of what the coadmissibility condition was. Coadmissible meant inverse limit of compatible coherent things. Now we have essentially inverse limits of bounded coherent complexes suitably interpreted. So we will denote this category of C complexes by D sub C of Dcap of X, because they very, very much look like complexes with coadmissible cohomology. This is not too difficult to do. This category is a triangulated subcategory because both the bullet points in my definition play immediately very nicely with distinguished triangles. If I have a C complex, then its cohomology is going to be coadmissible, right? Just from the definition, you can see how it is an inverse limit of the corresponding coherent guys. And moreover, if I look at a single complete Bornological Dcap module, so this is a complex concentrated in degree 0, then this is a C complex if and only if the module is coadmissible, right? Again, this is essentially straightforward. The second bullet point gives you one direction. For the second direction, so that a coadmissible module is actually a C complex, you need to show that the derived tensor products that show up here in the definition actually just give you something in degree 0. This is really just the usual tensor product in that case. Okay, very good. We have these three properties, but if you put these together, in particular property 1 and property 3, this is telling you, for example, that a bounded complex in this category is going to be a C complex if and only if its cohomologies are all coadmissible, right? Because you can repeatedly extend via distinguished triangles and argue by induction. So on the bounded level, this looks exactly like complexes with coadmissible cohomology. The only additional thing that shows up is basically that these things could be unbounded complexes, but they become bounded once we take the derived tensor product with Dn. Okay, so far everything I said is still assuming that my underlying base space X is an affinoid, but of course everything can now be defined globally by just saying that locally it needs to be a C complex with respect to some arbitrary affinoid covering. Okay, so now we have a well-behaved category of kind of complexes with coadmissible cohomology. Now, given that we also have these 6 operations, we can ask when do my 6 operations preserve C complexes? And just as in the complex algebraic world, where I told you in the very beginning, the 6 functors do not necessarily preserve coherence, obviously the same thing is going to be true here. These things are rarely stable under the 6 operations. There are a couple of exemptions where things really work quite nicely, and these are the stability properties with which I would like to finish. So the analogs in the complex algebraic world are that while coherence is not preserved under arbitrary inverse image, they are preserved under inverse image along a smooth morphism. And while coherence is not preserved under arbitrary direct image, it's preserved under direct image along a proper morphism. So we can do exactly the analogous theorem in this context as well. If I have any morphism between smooth, rigid analytic K varieties, if I impose that it is smooth, then the inverse image is going to preserve C complexes. If I'm insisting that the morphism is projective, that is, it's a closed embedding followed by a projection from relative projective space to the base space, then the direct image preserves C complexes. Of course, I would very much like to have this second point to read. If F is proper, then this works. I don't quite know how to do this yet. The proof strategy for this projective case is literally to split into the two cases, closed embedding and the projection map. And the projection map basically goes back to what I did in my PhD thesis. The direct image, the inverse image along a smooth morphism is essentially completely in parallel to how the classical, the complex algebraic case works. One needs to fiddle around a bit in making sure that one actually gets kind of exactness properties, but it's very much it's very close to the complex algebraic setting. Okay, and of course, so I should also say that the tensor product in the duality will also preserve C complexes, but this is something that is again essentially formal. Beyond this, as I said, to get stronger stability properties, one will have to talk about notions of holonomicity. There's at least some hope that there are some a framework that approximates the good conditions that we have, for example, for smooth complex algebraic varieties. But that's still in progress. So let me rather come to an end here and just say that we have indeed found a category that is large enough to allow for all these resolutions, sufficiently well behaved to allow for a derived formalism where we can derive all these functors, where we can then define the analogs of the 6 operations that we know from classical D-module theory. We can define this subcategory of C complexes as an analog of complexes with coherent cohomology, and these satisfy the same stability properties that we would find there as well. So inverse image along smooth morphism, direct image along projective morphism. Thank you very much for listening.